Hi everyone. Today we're going to talk about the Argand diagram. So back when we looked at polar form of a complex number, we talked about how we can plot points on a real and imaginary axis in the same way that we would plot points on a Cartesian plane with an x and a y axis. So the real part of our imaginary number goes on the real axis, same as the x-axis, and the imaginary part goes on the imaginary axis or the y-axis. So what we're going to do today is have a bit more of an in-depth look at what happens on the Argand diagram when we perform all the arithmetic that we've been looking at. So we're going to start with what complex conjugates look like on the Argand diagram. So the complex conjugate ends up being a reflection in the real axis, or the x-axis. So if I have the complex number 3 plus 4i, so across 3 on the real axis, up 4 on the imaginary axis, we know that the conjugate of 3 plus 4i is 3 minus 4i. And if I graph that on the Argand diagram, you can see it's just been mirrored in the real axis. So any complex number can just be reflected in the real axis to get the conjugate. We're also going to have a look at multiplication by I. So if I take that same complex number, 3 plus 4i, if I multiply by I, then I'm going to get 4i squared, so minus 4, and I'm going to get 3i. So minus 4 plus 3i is over in the second quadrant. So if this complex number is z, this is iz. And you'll notice that that is actually a right angle in between those two complex numbers. So a multiplication by I is an anti-clockwise rotation of 90 degrees. If I were to multiply minus 4 plus 3i by I again, I end up with minus 3 minus 4i. Or what I would get when I multiply 3 plus 4i by I squared, or negative 1. So this is I squared z, another right angle, or a 180 degree rotation, because a multiplication by negative 1 is a 180 degree rotation. And then I can do the same again and get 4 minus 3i, which would be I cubed times the original complex number. So every time I multiply by I, I'm just moving 90 degrees on my Argand diagram, because I'm switching real and imaginary parts when I multiply by I. Okay, when we talk about complex numbers on the Argand diagram, we often talk about them as vectors. So that's what I've been drawing here, is my arrow, which is a representation of that complex number as a vector from the origin. So if I have my complex number z, the vector form would be to put a little squiggle or a tilde underneath. So when I write it as an arrow vector, I'm talking about the position of the complex number. Let's say this was 4 plus 5i. This is the position vector. I could also have what's called a displacement vector, which may not necessarily be tied to the origin, but it's equivalent to that vector. So when I talk about a position vector, I'm talking about the position of that complex number from the origin, so the arrow that will get us from the origin to that complex number, and then the displacement vector, not necessarily tied to the origin, but going across 4, up 5, which will come into play when we look at subtraction. So, let's have a look at adding our vectors. So, for two vectors, if I'm adding them, then the position vector that I get is actually the diagonal of the parallelogram that we form. So if you know anything about vectors, you know that if I'm adding them, I just take one vector and put it head to tail with the other. So here, if I have the vector w that I'm adding onto z, I can just take w and move it to be at the head of z, and then this position that I get to, that is z plus w. So if I have 1 plus 2i plus 3 plus I know that that's going to be 4 plus 3i, and its position vector is just the diagonal of that parallelogram. And I could get the same thing by adding z onto w, putting that head to tail. So when I add them, I get the fourth corner, the fourth vertex of a parallelogram, if I include the origin as one of those vertices. When I subtract, I'll just write z plus w there so we know what it is. When I subtract, I actually get the other diagonal. So if I had z plus w over here, and I make this parallelogram, subtraction is actually going to be the other diagonal. And which way the arrow is pointing depends on which one goes first. So if I point the arrow at z, this is z minus w. And this is where what I was talking about with displacement vectors comes into play, because that vector actually has to be a position vector. So it actually has to start at the origin. Now I've lost a few bits of my complex number in there. Let me try and grab this exactly. There we go. So now it's a position vector. And if I look at my values, 1 plus 2i take away 3 plus I, it's going to give me 1 take away 3 is minus 2, and 2i take away I is plus I. And you can see that that is where that complex number is meant to be if I was just graphing minus 2 plus I. If I want to do w minus z, that is pointing the other way. So I'm going to move that vector down to be a position vector rather than a displacement vector. And I can check my numbers here. 3 plus I take away 1 plus 2i. Well, 3 take away 1 is 2. I take away 2i is minus I. And that's exactly where that vector is meant to be. And we know that z minus w is equal to negative w minus z. And you can see that if we were to multiply one of these by negative 1, we would get the exact opposite in the opposite quadrant, diagonally opposite quadrant, I should say. So subtraction is the other diagonal of a parallelogram, and the head of the arrow, the head of your vector, points towards the head of whichever vector came first. So if you're doing z minus w, the arrow points towards z. W minus z, arrow points towards w. Okay. If we are multiplying complex numbers, we're going to look at this in polar or in exponential form. So we know from our polar arithmetic that when we multiply two complex numbers, we multiply the moduli, but then the arguments are just added together. So what this means is if I have 2e to the I pi on 6 and 3e to the I pi on 4, my moduli, 2 and 3, are going to be multiplied together. So I'm going to get a vector double that long, because I'm doubling 3 to get 6. So it's going to be about that long. And I've put my complex number up there because I'm adding these two angles together, which gives me this angle. And I'm adding those angles because that's the argument. My rotation anti-clockwise from the x-axis. So that angle there is pi on 6. That angle there is pi on 4. And when I add them all together, I've got 5 pi on 12. So almost 6 pi on 12, which would be pi on 2, which would sit right on the imaginary axis. So I multiply the moduli, so however long those vectors are, I multiply that together. And all I do is add the arguments. So I just add those two angles from the real axis to work out where my vector will be positioned. If I'm dividing, I do the opposite. So we know when we divide two complex numbers in polar or exponential form, we divide the modulus and then we subtract the argument. So here if I have 4 and 2, 4 divided by 2 is 2, so I'll get a vector the same length as this one. And then I'm taking this angle and subtracting this one. So I'm going to end up with a vector, mine's not drawn particularly well, but pi on 3 take away pi on 4 is pi on 12. So it's going to be that same length and then somewhere down here. Because I just subtract those angles. So this angle in here should be the same as this one. Okay, that is multiplication and division. For powers of a complex number, we know that when we raise a complex number to a power, we raise the modulus to that same power. So if I want to work out what this complex number is cubed, then I would cube the modulus. So I'm going to end up with 2 cubed, which is 8. And then I multiply the argument by that power. So 3 times pi on 6 is 3 pi on 6, which is pi on 2. So I'm going to end up with a number right on the imaginary axis. 8 is pi on 2, and we know that if we work out cos pi on 2, that's going to disappear, so all I get is 8i, which is why that sits right on the imaginary axis. Okay, if we're not multiplying by a complex number, but we're multiplying by a constant, so we're just putting a number at the front, all that's going to happen is the complex number, the vector, will get longer or shorter if it's a positive constant. So let's say I want to take 2 minus I and multiply it by 2. All that's going to happen is that modulus is going to double, but the argument will stay the same. And if I worked it out in Cartesian form, 2 times that complex number would be 4 minus 2i. And you can see that line would have the exact same gradient, just be a little bit longer, double as long. If I was multiplying by a negative constant, the same thing happens to the modulus, but we know that a multiplication by -1 is the same as a multiplication by I squared. So I also have a 180-degree rotation. So if I want to multiply 2 plus I by -2, well, the modulus is going to double, and I'm going to end up in the diagonally opposite quadrant because I have this 180-degree rotation. So this would be -4 minus 2i. Okay, let's do one example just to bring this all together. So, given z and w, two complex numbers which are given here on my Argand diagram, indicate the position of the conjugate of z, 3 times w, negative 2 times z, z plus w, z minus w, w minus z, iz, z times w, and z divided by w. So we're basically going to put all the things we just learnt on one Argand diagram. I've got here the unit circle so that we know that when we're multiplying, our moduli are going to get larger because we're multiplying by a number bigger than 1. If w was within that circle, we would know that multiplying would make the modulus smaller because we're multiplying by a number smaller than 1. So where the unit circle is can have an effect on multiplying and powers. Okay, we'll start with the conjugate of z, and we know that's just a reflection in the real axis. So just down here, conjugate of z. Okay, 3 times w, positive constant, so w will just become 3 times as long in the exact same direction. Negative 2 times z, I know I'm doubling the length of z, but I've got a 180-degree rotation because I'm multiplying by I squared, or negative 1. Z plus w is the same as if I put w on the end of z, or z on the end of w. I might do that because I can be a little bit more accurate. So if I take z and put it head to tail with w, that tells me that z plus w goes just up there. So if I were to add both those extra vectors, I would have a parallelogram, and that would be the diagonal. Z minus w, I know that that's going to be the other diagonal pointing at z, because z came first. And then I move it to be a position vector. So if you're writing with pen and paper, you can probably just use your ruler to work out how long that vector needs to be, and then make sure it's parallel to that line, so that you can write it as a position vector rather than a displacement vector. And then w minus z, well, that is the same, pointing in the other direction, because if w comes first, it points at the head of w. Then I've got IW, which would be a rotation of 180 degrees. So same modulus, sorry, not 180, 90 degrees. So there'll be a right angle between W and IW. Z times W, I'm going to multiply the moduli. So W is only slightly longer than 1, which means Z will just get slightly longer. I have to add this angle to this angle. So when I do that, I'm going to end up somewhere over here, slightly longer than Z. Those two arguments added together. And then, lucky last, Z divided by W. I'm dividing by a number slightly bigger than 1, which means Z will get slightly shorter. And Z minus W, so if I start from where Z is and take away this whole angle there, I'm going to end up somewhere down here, kind of near the conjugate, slightly shorter because Z divided by W will be shorter than Z. Somewhere down there. So that is one example just to summarize everything that we've done. And these are what all our arithmetic looks like when we put it on the Argand diagram.